Proceeding to the second session of this FTB on data mining. To introduce our esteemed speaker for the session, now I request Ms. D. Angeline Jennifer, Assistant Professor from EC Department, to introduce the guest speaker of the session.
Good evening, all. I'm honored and privileged to introduce our resource person, Dr. Elias S. Cotricius, for today's session of 6 days online Atal Faculty Development Program on Smart Communication in IoT, Security and Future Applications and Possibilities. Sir is a distinguished academic researcher and leader in the fields of computer science, symbolic computation, and applied mathematics. His remarkable contribution to these fields have significantly impacted both theoretical advancement and practical applications. Dr. Cotricius has completed his doctorate in Department of Computer Science and he has a total experience of more than 25 years. He is currently a professor at Wilfrid Laurier University in the Department of Physics and Computer Science, Canada, where he has been a driving force in research and academic excellence. He has made sustainable contributions in various roles in different universities in Paris. With an extensive career spanning decades, he has made substantial contributions to combinational designs, optimization techniques, and symbolic computations. His work has led to numerous high-impact publications and conference presentations, reinforcing his role as a thought leader in the scientific community. He has received numerous awards and honors for his tremendous work in different areas. He has held various positions as senior editor, editor-in-chief, managing director in various editorial boards. As an esteemed researcher, Dr. Cotricius has collaborated with top institutions and scholars worldwide, furthering knowledge in applied mathematics and computational science. His expertise has earned him several honors, including the prestigious AAECC Best Paper Award and multiple merit awards from Wilfrid Laurier University and recognition from various academic societies. Beyond his professional achievements, Dr. Cotricius is a dedicated mentor and educator. He has supervised 60 graduate and doctoral students, guiding them towards successful academic and professional careers. His passion for teaching and research fosters an environment of learning and discovery, inspiring the next generation of scholars and scientists. Sir has shared his knowledge in more than 50 seminars and trainings. Sir is also an influential person in academic publishing and conference organizations. He has successfully organized 100 conferences. He has a wide range of publication of 88 journal publications and 35 book editions and 49 papers in referred conference proceedings. He has served on editorial boards of renowned journals including the Journal of Combinational Design and Journal of Symbolic Computation. Additionally, he has played a key role in organizing and chairing international conferences such as Applications of Computer Algebra and Conference Series, further solidifying his reputation as a global academic leader. He has an integral part in internal and external funding. We are truly privileged to have Dr. Elias S. Cotricius with us. His insight and experience will undoubtedly enrich our understanding and inspire us all to strive for excellence. Now, I request our resource person, Dr. Elias S. Cotricius, to take over the session. Sir.
Thank you very much for this really nice introduction. I appreciate it very much. It's an honor for me to be invited here. And I would like to start by thanking Professor P. Tsinia for the invitation and for guiding me through the process. So I live in Waterloo, in the province of Ontario in Canada, and Wilfrid Laurier University is an old university founded in 1911. So a few years ago, we had the 100-year anniversary of the university. And today I would like to discuss with you data mining. So I plan this talk as follows. I want to do a quick introduction to data mining, first of all. and describe, some specific tasks that can be done in data mining. Second, I would like to go into more depth into two of those tasks of different nature, and these are the classification problem and then the association rules problem. I also want to, at some point, make two remarks. These remarks are, I think, quite important. Um, if you ask a student, or whoever you like, what is the difference? What is the difference between data mining and some more developed area, for example, the area of databases? You will see that a lot of students, a lot of faculty even don't have a clear answer to this question. So they can't pinpoint particular concepts uh, that are different in databases and in data mining. So I also want to mention two answers to these questions, two very specific answers to this question. Why is data mining a different discipline than database? So this introduction here is taken from this very nice book by Tan, Steinbach, and Kumar called Introduction to Data Mining, one of my favorite books in data mining, if you like. So they start with this question: why mine data? And there are multiple reasons for that. First of all, there are a lot of data being collected and put in warehouses, so some sort of, if you like, extended databases with some extended functionalities. These data come from the web, from e-commerce websites. The typical example in data mining is the grocery store, the supermarket purchases. Consumers purchase goods at supermarkets. The banking sector, credit card transactions, and so on, all of that data collected by the banking system, the financial system more generally. So all of this proliferation of data, this so-called data deluge, if you like, um, um, created this need to mine data. From the scientific viewpoint, there are new technologies emerging: drones, satellites, microarrays generating gene expression data, scientific simulations generate terabytes of data, and so on and so forth. In the medical professions, of course, we have a proliferation of data from hospitals and elsewhere. So let me skip a few things. So data mining is a part of a larger process called KDD. KDD means knowledge discovery in database. And one definition of data mining is that it's the non-trivial extraction, I would add algorithmic extraction, of implicit, previously unknown, and potentially useful information from data. And as I said previously, I will give specific examples of why this is different than the traditional database approach, whereas, we have the SQL language, the structured query language, right? And we can also discover patterns in data using this SQL. The second definition of data mining is the exploration and analysis by algorithmic means of large quantities of data in order to discover meaningful patterns. And here I want to make clear what is the difference between this definition and the traditional database approach to answering queries, database queries using SQL. The difference is that data mining is able to discover patterns that cannot be discovered with database. So that is the first important point I want to make. There is a fundamental difference between data mining and database. That is why data mining is a separate discipline altogether, because we are able, with data mining, to discover patterns in the data that we cannot discover using structured query language or SQL. Okay. So let me come back to this diagram here. You see that over here we have the data, the raw data. Then we select some of it. This is our target data. We do some pre-processing, typically some transformation. Then we apply data mining because the data has to be put in a format that is amenable to data mining algorithms. We cannot just apply a data mining algorithm to any data. The data has to be in a particular format. So we have all these steps. Then we apply data mining. We discover these patterns, and then we evaluate and interpret these patterns, and we end up with knowledge that we extracted from the data. So this is the entire process around data mining. Now, the origins of data mining are the following. It draws ideas from machine learning, from AI, from pattern recognition, from statistics, and of course, most of all, by database systems. And the idea, again, is the same, that the traditional techniques that we used to use to analyze data in statistics, in pattern recognition, which is a very well-developed area, and of course in database systems, they are unsuitable to perform this extraction of patterns because of the enormity of data, because of the high dimensionality, uh, and because of the heterogeneous or distributed nature of data. Data can be stored in various different locations. Okay, so there are two broad categorizations of data mining tasks. The first one is the so-called predictive or prediction methods, where we use some variables, some features of the data to predict unknown or future values of other variables. And then we have the description methods that differ from prediction methods in the sense that they are concerned with finding human interpretable patterns that describe the data. For example, a cluster. Let's say you have your points and they are clustered. This is a human interpretable pattern. Okay. So these categories are further subdivided into six basic data mining tasks. So pretty much all of data mining, or 90% of data mining, revolves around this developing efficient algorithms for these six data mining tasks. So we have classification, which is a predictive data mining task. We have clustering, which is descriptive. We have association rules mining, which is again descriptive. We have sequential pattern discovery, which is descriptive. We have regression, which is also well known from statistics. This is a predictive data mining task. And we have deviation detection, so outliers, which is a predictive data mining task. So we have 6 predictive and 6 descriptive tasks overall in data mining. And as I mentioned, I want to focus on one predictive task, the classification, and one descriptive task, the association rule discovery. Okay. Yeah. So let me open another PDF. So we're going to start with decision trees classification. This is one way to do classification. There are other techniques, and something that I forgot to mention in the previous slide is that for every one of these 6 data mining tasks, there are several different algorithms that have been developed since 1990, which is about the time where data mining started to become a separate discipline in itself, around 1990. And here we are 30, 35 years later or something like that with data mining being an entirely different discipline within computer science with several applications in pretty much everywhere, in every domain that you can think of. So I want to discuss decision trees classification and illustrate what are decision trees. I'm going to skip some of these overheads because they're the same. This is by the way, the KDD process, the knowledge discovery in databases. It is a more general process. I showed you this diagram previously, and data mining is a part of it. So in data mining, we also have the concept of learning, which is a very complex process. And we can distinguish 4 levels of learning. We can learn facts, so simple statements or truths. We can learn concepts, which means sets of objects, symbols, events grouped together because they share common characteristics. We can also learn procedures and principles. So here are 3 different perspectives for concepts in data mining, and I want to illustrate them with examples. There is the classical view where concepts have some definite defining properties, and these properties determine whether an individual data item is an instance of a particular concept. For example, here is a rule for good credit risk that is used. This is a contrived primitive example, artificial example, right? But it's similar to what they use. A rule for good credit risk is the following. If annual income is less than or equal to 30,000 and the number of years working is bigger than or equal to 5 and owns a home, then true. Then good credit risk is true. So all 3 conditions must be satisfied for the applicant to be a good credit risk. So the algorithm here is very simple. We just look at the 3 conditions of the if statement. If they're all satisfied, then the algorithm says outputs true. And you get a loan, let's say, if you're asking for a loan at the bank. But there is also the probabilistic view. Now concepts are represented by properties that concept members probably satisfy. So people store or recall concepts as generalizations created from individual observations. For example, here's the probabilistic view of what it means to be a good credit risk for an individual to have a good credit rating. The mean annual income of people who consistently make loan payments on time is 30K. Now, we're not saying the annual income is bigger than or equal. Now, we're saying the mean annual income is 30K. Most good credit risks have worked for at least 5 years. Again, a different statement from this strict inequality up here. And finally, the majority of good credit risks own their own home. So the definition offers some general guidelines about the characteristics of a good credit risk and cannot be directly applied to find whether a person is a good credit risk or not. And finally, we have the how do we make this definition operational? Well, how can we use it to help with the decision-making process? Well, we associate a probability to it. So, for example, $27,000 years working, 4 owns a home is 0.85%, and we use a threshold value. If this probability is bigger than the threshold value, then this is a good credit risk. Otherwise, it isn't. And finally, we have the exemplar view, which is described here. Now, a given instance is determined to be an example of a concept if it's similar enough to a set of known examples of that concept. So people store and recall likely concept examples that they use to classify new instances. Here's an example. A possible list of 3 examples considered to be good credit risks is given over here. Example 1, example 2, example 3, with that particular data, 32K, 6 years working, owns a home, 52K, numbers of year working, 16, etc. That definition can help with the decision-making process, again, by associating a probability and deciding whether or not an example number 4, a fourth individual, can be classified as a good credit risk or not. Okay, so these are the concepts that we are going to be using in classification. So we have supervised learning. Supervised learning is a twofold process, which I'm going to illustrate quite specifically in today. So first of all, we build a model, and second, we use a model to classify new instances and to predict the value of the classification attribute. So the question that arises is the following basic question in decision tree classification. How can we develop a generalized model to represent some given data to solve this number 1 phase and then use this model in phase number 2? Okay, and one answer to this question is the concept of the decision tree. So let me illustrate the concept of a decision tree by an example. Here is a hypothetical data set for disease diagnosis. Every row, except for the first one, is an instance of data. So the first row is just the metadata, if you like, the famous metadata that we read about on the internet and in the news. So the patient ID, we have 6 patients, 1, 2, 3, 4, 5, 6. Then fever, congestion, headache, and finally the diagnosis. It turns out that these 3 attributes of the data, fever, congestion, and headache, are binary. So they have values yes or no. These are the symptoms that the doctor is able to record. And based on those symptoms, we also have the value of the diagnosis attribute, which is the classification attribute. So allergy, cold, allergy, and TB, tuberculosis. So this table is given in the attribute value format, which is familiar from RDBMS's, Relational Database Management Systems. We have 3 input attributes, fever, congestion, and headache. So we have the possible symptoms experienced by individuals suffering from either from allergy or cold or TB. And the output attribute is the diagnosis. So we want to predict the value of this attribute for patient number 7, 8, and so on, where we only know the values of the input attributes, but we don't know the value of the diagnosis. Okay, that's the idea of decision tree classification. And so what is the model? How do we take this data over here and summarize it or generalize it, if you like, into a model? And what is a model? So a model can be a so-called decision tree. So a decision tree is a tree in the usual sense of computer science, where a terminal node, a leaf node, represents or reflects a decision outcome. A decision on what? On the classification attribute, a value of the classification attribute, and internal nodes represent tests on one or more of the input attributes. Okay. So decision trees are easy to understand, and here is one of them. Here's a decision tree for the disease diagnosis data in the previous example. What we do is we start at the root node. We look at the attribute fever. We know there are only 2 values. It's a binary attribute, yes and no. And if the value of fever is no, then we conclude immediately that the diagnosis is allergy. So if we go back to the data, indeed, if fever is no over here, then diagnosis is allergy. Fever is no, then diagnosis is allergy. Fever is no, then diagnosis is allergy. Okay. So we are able to represent 3 of the 6 data with this part of the tree. Now, if the value of fever is yes, it turns out we cannot classify the remaining data right away. We have to look at the value of congestion. And if the value of congestion is yes, then the diagnosis is cold. If the value of congestion is no, then the diagnosis is TB. So this is our decision tree. This is our model of the data. There are many terminologies for this. We call it the summarization of the data or a model of the data. So we solved phase 1, and now we can use this model to complete phase 2 of classification, which is to use this model to predict the value of the classification attribute, the diagnosis, okay, using the decision tree for patient number 7, 8, and so on, where we only know the values of the input attributes, fever, cold, and digestion, fever, congestion, and headache. I'm sorry. By the way, note that the headache is not used. The attribute, the input attribute headache is not used in the decision tree. So not all of the attributes have to be used. Okay. The only thing that I didn't tell you is how we make this decision tree, right? How from this disease diagnosis data that we have, we ended up with this decision tree. Well, this is done. There are some of the first algorithms that existed to do this are called C45 and ID3. So I want to discuss ID3 in more detail, and C45 is a more sophisticated version of ID3. So here's the ID3 algorithm and the ideas behind it. It's called ID3 because it stands for this cryptic acronym, iterative dichotomizer. So iterative dichotomizer means that it dichotomizes, it splits into 2 the data set, and it does that iteratively. And the main idea behind it is the idea of entropy used in information theory. So let's try to explain this this idea. It amounts to this: ask questions whose answers provide the most information. As an example, question 1: when we ask about a certain entity, is it an animal or not an animal? Then we divide the search space of our data into large domains, which are pretty much balanced. But if we ask, is this particular data item, is it my brother? Okay, then there is practically no division at all in the data, because I may have 1, 2, 3, 10 brothers, but not hundreds or thousands. So most of the data items are going into the second category of not being my brother. Therefore, the probability of occurrence in Q1 is that we almost have equal probabilities. But in Q2, one set has a very small infinitesimal probability, the brother, and the other one has a very large probability. Therefore, the basic strategy of ID3 is to choose as a splitting attribute the one with the highest information gain first. What is the splitting attribute? The splitting attribute is, this one here, the root attribute. So we choose that one first, and then we classify those data items that we can. And for the other ones, we do the same thing recursively. So we find another splitting attribute and so on, and we do that recursively. That's how ID3 works. So let me remind you a bit some formulas regarding probabilities and entropy. So entropy is used to measure the amount of uncertainty or randomness in the data. If your entropy is 0, then there is no randomness at all, and that means that all data belong to the same class. and that means that there is no more classification to do. So the objective of decision tree classification is to iteratively partition the given data set into subsets so that all elements in its final subset belong to the same class, and therefore there is no more classification to do. So now this formula is well known. Given probabilities P1, P2, Pn, the sum, of course, must be equal to 1, and the entropy of these probabilities, this capital H, P1, P2, Pn, is the sum of the probabilities times the log 1 over Pi, or this is more familiar, minus the sum of Pi log Pi. This is a well-known property of logarithms that we use here. Now, this entropy has this nice property. It is maximized when all of the Pi's are equal to 1 over n, so all of these events are equiprobable. Now, how do we use this entropy ideas into our algorithm to create a decision tree? Well, suppose that we have an initial set T of training samples or tuples. Each one of them belongs to one of the k possible classes C1, C2, Ck. Then for a subset S of these tuples from T, we denote by PCIS the number of samples in S that belong to class Ci. Of course, we know that the sum of all of these numbers must be equal to the cardinality of S. Okay? Now, what is the gain criterion? The gain criterion is used to select which attribute from the input attributes will be the splitting attribute. First of all, we compute the entropy of the set S of tuples like this. H of S is H of these probabilities. So we divide these numbers that we just defined by the cardinality of S and make them probabilities. Of course, they sum to 1. And if the test on the splitting attribute X has n outcomes, then T, the set of tuples, is partitioned in n subsets T1, T2, Tn. Then we compute the entropies of these subsets of tuples with the same formula as before, this formula here, right? But now we do it within this set of tuples T1, T2, Tn that have the property that they have the same outcome for the classification attribute. And then we form this weighted sum over here of these entropies of the Ti weighted by these coefficients, the cardinality of Ti divided by the cardinality of T. And now we're ready to define the gain criterion. The gain in information by partitioning T according to X, the splitting attribute, is denoted like this. Gain of X is H of T, the entropy of the entire set of tuples, minus Hx of T, which is, again, the weighted sum of the entropies that result from the specific splitting of the T tuples according to the n outcomes of the X attributes. And we do that for all the input attributes, not the classification attribute, of course. So when we do that, we compute the gains, and the gain criterion tells us the following. We select as a splitting attribute, so where to start the root of the decision tree, the attribute X, that maximizes this quantity, gain of X. Okay? And as I said before, we do this recursively until we reach the leaves of the decision tree. So let's try to illustrate this process with a specific example of data. In this example, we have 3 input attributes, attribute 1, attribute 2, attribute 3, and the classification attribute, which happens to be binary, class 1 and class 2 values, right? Attribute 1 is ternary attribute ABC, the values are ABC. Attribute 2 is a categorical attribute, there are many values, okay? And attribute 3 is a binary attribute, true and false values only. To begin running this algorithm, we have to compute the entropy of the starting set T, where the classification attribute is the class attribute. So this last one over here, the fourth column. So what do? Well, we look at the probabilities P1 and P2. P1 is 9 over 14. There are 9 class 1 values, and P2 is 5 over 14. There are 5 class 2 values. So using logarithm base 2, in these 14 tuples, we split them at 9 as 9 and 5. So h of t is h P1, P2. We write down this formula with these two probabilities, P1 and P2, and we find 0.94. Okay, so this is how we compute the entropy of the starting set. And now we have to start computing the gains using the formula that I told you about that uses HT, of course, so we have to compute HT. So we use attribute 1, attribute 3, and attribute 2, the 3 splitting attributes. We're going to compute the gain criterion for each one of them. And based on the gain criterion, we're going to use the attribute for a splitting attribute for the root of the decision tree, the one that maximizes the gain. So using attribute 1, we divide the initial set T into 3 subsets, K equals 3, T1, T2, T3, correspondingly to the 3 values A, B, and C. There are 5 A tuples, 4 B tuples, and 5 C tuples for attribute 1. Okay, so this is H of T1 over here. Again, we compute the probabilities, but now within T1, T2, and T3. So there are 2 values, 2 over 5 and 3 over 5. And the sum, of course, is 1. And this is the entropy, 0.97. H of 2t is 0. Oops, maybe that's a typo, right? What does that mean? Let's go back here. What does it mean that h of t2 is equal to 0? Well, if we look at these 4 values here with b, t2, remember, are the data that have the value equals b. There's 4 of them, these 4 tuples over here. These 4 tuples have the value b for attribute 1, and the class attribute has the same value, class 1, class 1, class 1, and class 1. Therefore, we have nothing to compute. There is no entropy. Entropy is 0. All these T2 tuples are classified as class 1. So we are done. This is a leaf. This is a leaf node in our tree if we use attribute 1 as a splitting attribute. And HT3 is, again, we use this formula, and it's the same entropy, 0.97. Now we can compute the H attribute 1 of T by the previous formula, the weighted sum, and we get 0.69. And now we can compute the gain of attribute 1. It's H of T minus the weighted sum, 0.24. Okay. Now we're going to use attribute 3 to divide the initial set of tuples into 2 subsets. Why is it 2? Because attribute 3 is a binary attribute. So we only have 2 classes, T1 and T2. We compute again the entropies over here. The entropy here is 1. This is also an interesting number. What does it mean exactly? Well, it means that the number of the values is equidistributed, if you like. HT2 is this one here, 0.8. Same formula for H attribute 3 of T. And finally, the gain of attribute 3 is given by this difference, 0.048. If we compare it with this value, we see that clearly between attribute 1 and attribute 3, the one that maximizes the gain is attribute 1. So attribute 1 is a splitting attribute. Okay? But we also have attribute 2. And for attribute 2, which is a categorical attribute, well, we use a threshold value, and we use the midpoint of values as the threshold. So for example, in this particular data set, we have m equals 9 values. So here they are. And what we do is that we put the threshold somewhere in the middle here, 80. And this is our test to use to make the classes. If attribute 2 is less than or equal to 80, then we call this class 1 or T1. And if attribute 2 is bigger than 80, then we call this T2. So we have two sets again, and we can compute using the same formulas. We compute the gain of attribute 2, it's 0.1. And remember, the gain of attribute 1 is bigger than that. So based on the gain criterion, the algorithm still selects attribute 1 as a splitting attribute. So this is phase 1 of the algorithm. And this is we're beginning to construct our decision tree. Attribute 1 has been identified as the splitting attribute because it has the highest gain. Okay. So the test on attribute 1 is whether its value is equal to A or B or C. So we split the 14 tuples into these three sets over here. And what do we notice? We notice that over here we finished the classification. All of the data values have the same value for the classification attribute, so we are done. But here we are not, so we have to do the same thing recursively in this smaller set of tuples where we have deleted attribute 1 because we know its value, it's always equal to C in this particular part of the tree. And over here we still have a class 1 and class 2 intermingled. Therefore, we have to use this algorithm recursively. So we repeat the process for all three children nodes. In fact, only two, this one and this one. The node in the middle is a leaf node because, again, the values of the classification attributes are the same. So we achieved classification. There is nothing else to classify. So this is the final decision tree after performing one more iteration, right? Iterative. Remember, we are iteratively dichotomizing, splitting into two or more the value, the tuples in our data set. So this is the final decision tree. These are the leaf nodes, class 1, class 2, class 1, class 2, and class 1. To find those two leaf nodes, we have to look at the value of attribute 3. This is the splitting attribute over here. And over here, attribute 2 is the splitting attribute. And we use a test on some median value, the 70 in this case. So we have 5 leaf nodes and we are done. This is our final decision tree. And now I want to illustrate the phase 2 of classification, which is to use the decision tree to predict the value of the classification attribute based on this model, this generalization of our data. Okay, I will skip some things here. These are some optimizations, if you like. So this is another data set, which is a bigger one with 5 input attributes and 1 classification attribute, the diagnosis. If you run the ID3 algorithm, then you will find this very small decision tree that uses only two input attributes from the 5 and still manages to predict the diagnosis correctly. Okay, so you can contrast this idea with the so-called feature selection in machine learning. When you have a high-dimensional data set over here, you have five input attributes, but it turns out that only 2 of them, the swollen glands and the fever, are important in order to build your decision tree. And now we're going to imagine that we have data instances with an unknown classification. So 3 more patients, 11, 12, and 3, with these values for the input attribute, and we want to predict the value of the diagnosis attribute based on the decision tree. So we remember we have to look at the value of swollen glands. So when we do that, when we see a no over here, When we see a yes, sorry, we know that the diagnosis is strep throat. So there it is. We see a yes, therefore the diagnosis of patient 11 is strep throat right away. When we see a no, then we have to look at the value of fever. If the value of fever is yes, okay, so let's do that. The value of fever is yes over here, swollen glands is no. Therefore, the diagnosis of patient number 12 is cold. And in the other case, the diagnosis is allergy. So this is a complete, fully illustrated example of classification using decision trees. I remind you there are two phases. There is a phase of um, uh, building the model of your data. In this case, the model is a decision tree. It could be something else, okay, but in general, but in this particular case, it is a decision tree. And phase number two is use the model, use the decision tree to make predictions for data items like these with unknown classification. Okay, this is what we mean by classification using decision trees. Again, this algorithm ID3 is one of the very first known algorithms to do that, to build decision trees. There are many improvements since then. There are entire books, devoted to the theory behind decision trees and other more sophisticated algorithms to build decision trees. It's becoming a mini sub area, if you like, within data mining. Now, of course, with the advent of big data, it was realized that although the computational complexity of these decision tree algorithms is relatively low, you can still run into problems when you have big data, large data sets in the realm of big data. For example, your algorithm, your implementation that runs very nicely in these small examples that I showed you, or maybe a couple of hundred data items, will not work when your data set is 1 terabyte or something like that. And it turns out that in this day and age, there is no shortage of data sets that are a lot bigger than terabyte in many areas. For example, in astrophysics and in many other areas, that they have at least petabytes of data sets as orders of magnitude. In bioinformatics, there are 90 million different databases, so it's an unbelievable number of different databases. And researchers are looking to sequence the genome of organisms and so on, so huge databases. So there are some improvements of these methods, how to build decision trees for big data sets. I just want to mention a few things here, give some references. There is this PhD thesis in 1991, machine learning on very large databases. The issue here is that the entire data set has to be loaded into the main memory before the induction. Therefore, the size of the data sets that can be processed by this algorithm is bounded by the memory size. But it is progress, definitely, as opposed to a simple implementation of ID3. Then we have this 1992, another PhD thesis from ANU, probably the best university in Australia. Fifield suggests parallel implementation of the ID3 algorithm. And the same assumption here, the entire data set has to fit in main memory, which is not a desirable feature, but again, it is progress as opposed to previous algorithms. By the way, the parallel implementation here is not obvious because ID3 is a recursive algorithm, and recursion and parallel programming don't like each other very much, right? So you have to You have to put some extra effort into doing that. Then scalable data mining, 1997. What they do is to partition the data sets into several disjoint data sets so that each one of them is loaded separately into memory, do a decision tree, and then combine the decision trees to create a single decision tree. It's not too easy, as you can imagine, but again, it is an improvement over the previous serial implementations. Disk-based approaches. Okay, there are many other things here. There is something called Rainforest. It's a framework for decision tree classifiers that is capable to scale any specific algorithms from the literature, including C45, CART, and CHAID. There are many, tons of algorithms. I think I will leave it at that for as far as decision trees go, and go on to the third part of my presentation, which has to do with, as I promised, with association rules in data mining. Okay, this is another very big area in data mining, which is driven by practical considerations. So what is an association rule in data mining? Well, it's an association rule is something that shows a relationship which is not inherent in the data between data items. As an example, we can write down a very simple association rule. If a consumer goes into a supermarket and purchases product A, then with a high probability, they will also purchase product B. Okay. This concept is reminiscent of the concept of functional dependencies in database theory. And this is the second point that I want to mention. Remember, I was asking this question in the beginning: why is data mining a different discipline from databases? And I gave you one answer already, and this here is the second answer. The second answer is that although this concept of association rules in data mining is very reminiscent of the concept of functional dependencies from database, they are not the same. Okay? Huge fundamental difference between data mining and database. Why they're not the same? They're not the same because of the very simple fact that if you recall functional databases from relational database theory, functional dependencies are relationships that hold in the data, but they hold 100% with 100% certainty. Okay? The data in relational database must obey this particular relationship 100% of the time. There are no exceptions. Here in data mining, we have a probability. Purchase product A means with a certain probability, which may be low or high, we purchase product B. So it doesn't mean that all of the data items satisfy this relationship. They don't, right? Therefore, there is a fundamental difference here between data mining and database that it's good to be able to explain to students in a very specific context why database and data mining are not the same thing. So association rules are different from functional dependencies because they hold with a certain probability, while functional dependencies hold with 100% certainty. If they don't hold in a set of data, then this is this is not a legal database state, as we say in the relational database theory terminology. So association rules detect common usage of items They do not represent causality or correlation. It's just a frequency consideration. And in the context of association rules mining, what we do in most cases is that we look at the database as a set of transactions, each transaction involving certain items. Okay, that's the terminology. And in fact, this terminology is called market basket data model. So we mine for association rules. We're looking for association rules in data using this format of the market basket data model. So a market basket corresponds to the set of items a consumer purchases during one visit to a supermarket. It's something that we can all relate to. It's a very simple model, right? But its power stems from its simplicity. The set of items purchased by customers is known by this term over here, item set. And an association rule that we abbreviate as AR is of this form over here. X determines Y, if you like, where X is X1, X2, Xn is an item set, and Y is Y1, Y2, Ym is another item set. And where the Xi and the Yi are distinct items for all I and j. This association rule is also noted as left-hand side implies right-hand side, and the reason for that will become apparent in the next few overheads. So this association rule states that if the customer buys X, the item set X, the set of N data items X1, X2, Xn, then they are also likely with a certain probability to buy Y, the set of Y1, Y2, Ym items. Okay. The item set of the association rule is the union of the left-hand side data items and the right-hand side data items. Now, not all association rules are interesting, right? The ones that are interesting are measured by the so-called support and confidence. Okay? So let's describe these two concepts, the support and the confidence. First, we denote an association rule by left-hand side implies right-hand side. Now, what is the support and then what is the confidence? Let's start with the support. The support of an association rule is the percentage of transactions that contain all of the items in the item set of the association rule, i.e., the left-hand side union right-hand side. So this refers to how frequently this specific combination of item sets, the left and the right-hand sides, occur together in the database. If the support is low, if this number is low, okay, it's a percentage. So if this percentage is low, then this means there is no overwhelming evidence that items in this item set occur together, i.e., this association rule here is not a plausible association rule. So that's why the support is useful, because we compute this support, and if the support is small, then, well, we're not interested that much on this association rule. We can prune, if you like, this association rule from consideration and continue with other ones, more promising association rules. So the confidence of an association rule is the conditional probability that the items of the right-hand side will be purchased when the items of the left-hand side are purchased. So this one measures the strength of the implication left-hand side implies right-hand side. How do we compute it in practical terms? We can use the definition, so from all of the transactions containing the left-hand side, how many contain the right-hand side, okay? Or we can use this formula. The confidence is a ratio of supports, the support of the item set divided by the support of the left-hand side only. So there are two alternatives, which are equivalent, of course, that help us to compute. When you program this algorithm that we will see in a minute, then you can choose which one of these two methods you're going to do. In other words, it's just counting, simple counting on your data set. So here's an example. I'm going to illustrate this concepts with an example, a very small example of four transactions. So the transaction IDs here are part of the metadata. The time is also part of the metadata, and this is not considered at all in the algorithm. We are only considered with the actual data sets given as a set of items purchased by one visit by one client at a supermarket. So the first client bought milk, bread, cookies, and juice, the second milk and juice, and so on. Now, consider two plausible potential association rules. Milk gives juice and bread gives juice. And their supports are 50% and 25% respectively. Why is that? Because if you look at the first one, milk and juice, these two items appear together in 2 out of the 4 transactions, so 50%. The bread and juice, this particular combination of data items appears together in 1 of the 4 tuples, so 25%. The support is 25%. Now, what are the confidences? The confidences are 66.7% and 50% respectively. Why is that? Well, let's look at the first one. Milk implies juice. What do? We count all the data, the data that contain milk. There are 3 of them. And we see that in 2 out of the 3, we also have juice. So 2 out of 3, 66.7%. And for bread juice, well, there are 2 transactions that contain bread, and in one of them we have also juice. The first one, this one here, in this one here we don't, therefore 50%. Okay, so this is a simple example of the kind of counting that you have to do to compute supports and confidences for any association rule based on your data. The goal of mining association rules is to generate association rules that exceed some user-specified support and confidence thresholds. Remember, we said that not all association rules are interesting. Interesting are the ones that have a big value for the support and more importantly, for the confidence. Okay. So let's see how this is done. This is a general 2-step algorithm to generate association rules. The first step is the following. You generate all the item sets, all the sets of items that have a support exceeding the given threshold. Items with this property are called large or frequent item sets. That's the terminology that we use in data mining. So a large item set or a frequent item set is an item set that has a large support. And what does that mean? It means that the support is bigger than the user-specified threshold for the support. So typically we use a support bigger than 50%, at least. It must be at least 50% or 75%, right, to make it interesting. The second phase is you generate rules for each large item set as follows. For a large item set X and Y, a subset of X, we let Z or Z, depending on where you live, okay? My American colleagues want me to say Z, and my Canadian colleagues, of course, say Z. So in any case, let Z or Z be the X minus the Y attributes. And now we have this criterion. If the support of X divided by the support of Z or Z is bigger than the minimum confidence, then this rule over here, Z implies Y, i.e. X minus Y implies Y, is a valid association rule. Okay, that's the criterion. Now, I have a quick question for you. Which one of those two phases do you think is more computationally expensive, the first one or the second one? May I have some feedback, please, on the chat? So let me repeat my question. Which one of those two phases, phase one or phase two, do you believe is more computationally expensive in your algorithm, in your implementation? Okay, we have an answer by Sandeep. Thank you, Sandeep. Phase two. Okay, anybody else? Ayesvaya says Arumugam, phase two. Okay, so we have phase two. We have three takers for phase two. Four Sasikala, thank you, phase two. Okay, anybody else before we move on? Phase two. Okay, well, that's overwhelming support. I see a lot of Sujata, Bano. Okay, phase two. Right. Okay. A lot of you are. Everybody is saying phase two. In fact, it's phase one. Phase one is more computationally expensive, and I will explain why. So, generating rules from large item sets, once we found the large item sets, is relatively easy. Discovering the large item sets, so phase one, is hard. And why is that? Because we have exponentiality. We have an exponential explosion of the number of possibilities. And this is because when we have m items, okay, m items, then the number of item sets, possible item sets that we have to examine is 2 to the m. Therefore, according to the binomial theorem, you know that this is an exponential number, the sum of all these possibilities, right? It's the binomial coefficients. So how many item sets of size 2 do we have? Binomial coefficient m choose 2. How many of size 3? M choose 3. And the size of all these binomial coefficients, as you know, is equal to 2 to the m. Therefore, we have an exponential number of item sets to choose from. Therefore, this is a computationally expensive procedure. However, the magical property, if you like, of the algorithm that we will see in a minute is that it uses these two properties. It uses these two properties to effectively reduce the combinatorial search space for association rule generation and for large item set generation, right? And these two properties are the downward closure and the anti-monotonicity. So let me describe those two properties. What is the downward closure? It's the following idea. A subset of a large item set must also be large. In other words, subsets of large item sets exceed the minimum support. And that means that if I find a large item set, then I know, I have that information, that every one of its subsets of any size must also be large. Okay? This is easy to prove. Of course, you can think about it and prove it. This is the downward closure. And then we have sort of the dual property, the anti-monotonicity property, says the following: a superset of a small item set is also small. Again, easy to prove, but very very important property. So if the item set does not have sufficient support to be considered for rule generation, it's a small item set, then any one of its extensions by any of the data items is also small automatically. Therefore, it turns out that a combination of these two properties allows us to prune this huge combinatorial space of 2 to the m and discover large item sets, and then go to phase 2, where we actually discover the association rules with big confidence and big support. Okay, so it's a beautiful algorithm, absolutely beautiful algorithm, allows you to deal with, you know, a 2 to the m space. If m is, let's say, you know, 30, then you can probably do an exhaustive search on a large computer. If m is 40, 2 to the 40 is still manageable on a supercomputer. But if m is 100, then forget it. There is no way to do the enumeration of the 2 to the m item sets efficiently. However, using this downward closure and anti-monotonicity properties, it turns out that the pruning of your space is so effective that you can deal with, you know, m is 100 or more. It's difficult to believe, right? But again, those two properties are so efficient that make this algorithm work very well in practice. And this is the so-called a priori algorithm, the very first algorithm to generate association rules. Since then, there are many other algorithms, the partition algorithm, which builds a tree recursively and so on, but a lot more complicated than the a priori algorithm. There are maybe now at least 10 different algorithms to generate association rules, each one with their own optimizations and improvements. So the a priori algorithm was the first algorithm used to generate association rules. It uses this general two-step algorithm that I described for creating association rules. But the key point is that it's doing that together with these two properties, downward closure and anti-monotonicity. Okay, that's the key point that makes this algorithm work. So this algorithm is here. This is the input is a database of m transactions. So we again use the market basket data model, right? A minimum support, min s, a value, which is a fraction of m, the number of transactions. And the output is the frequent or large item sets. They are arranged in a list like this one, L1, L2, Lk. What is L1? L1 is the list of one item sets, so item sets that have one item. L2 is the list of frequent or large two item sets, so item sets that have two items. And finally, up to Lk. The number k is experimentally determined within the algorithm. It's not part of the output, right? But we know that there is a finite number. We cannot, you know, we can only have, when we have m transactions, and when we know the number of different data items, then we know that this is an upper bound for k. So we know that k is a finite number. We will see how it's determined in this algorithm. So the first step is to compute the supports of all the individual data items, ij. So this is the count of ij divided by m. And we do that by scanning the database once and counting the number of transactions where this item appears. Then we put all of these frequent one item sets in the list C1, which it will be initially all these items I1, I2, IN. And now we check which ones of those satisfy this inequality. The support is bigger than minimum support. And this is the L1. This is our first part of the output. L1 is the list of frequent or large one-item sets. Now we go into a repeat until loop where we create LK plus 1. Initially, it's empty. How do we find, so K is 1, and now we're making L2 over here, LK plus 1, and at the end we increment K if we have to, if LK plus 1 is not empty. If LK plus 1 is empty, then we're done, and we determine K experimentally. So create the candidate frequent K plus 1 item set CK plus 1 list by combining members of LK that have K minus 1 items in common. So we form candidate frequent K plus 1 item sets by selectively extending frequent K item sets by one item. In addition, if here we use this is described explicitly here, but implicitly we're using the two properties, the downward closure and anti-monotonicity. So I would like to illustrate this algorithm with the same data set that we have over here to give you an idea how it works. So we're going to run the a priori algorithm on the data that we have. Let me make this a bit bigger. The minimum support is 0.5. M is 4. We have 4 transactions. N is 6. What is N? N is the number of different data items, and we know that we have milk, bread, juice, cookies, eggs, and coffee, and this is your C1. This is the list of candidate one item sets. Okay. Now we count the supports: 0, 75, 0, 5, 0, 5, 0, 5, 0, 75, 0.25. And we realize that we will only qualify for L1, the milk, the bread, the juice, and the cookies, because the other two, the eggs and the coffee, they don't exceed the minimum support, which is 0.5. So we get rid of eggs and coffee, and we keep, this is L1. L1 is milk, bread, juice, and cookies. It's pretty simple, right? And now we're going into the repeat until loop. The first iteration of the repeat until does the following. We're going to extend frequent one item sets, so M, B, J, and C, to create candidate frequent two item sets, and then count the supports. So here is the extensions that we can do. We can extend milk with bread, milk, juice, bread and juice, milk and cookies, bread and cookies, all the combinations, juice and cookies. Okay. We count the supports. These are the numbers, and we see that only these two qualify for L2. So L2 is these two. The list of large two item sets with two items is this one and this one. Okay. Therefore, here's a question. Why didn't we include M, E, milk and egg, into C2? Well, because E is a small item set. Therefore, by anti-monotonicity, this is also small. Any superset of small is also small. So we don't have to compute anything here, no support, no nothing. We know, just because of the anti-monotonicity property, we know that this cannot be part of C2, let alone L2, right? So all the other combinations are disqualified based on the anti-monotonicity property. So you see the kind of pruning of the search space that is achieved via this anti-monotonicity property. Now the second iteration of repeat until, we're going to extend frequent two item sets to create candidate frequent three item sets. But we see that there is no extension of L2 item sets that can be a frequent three item set. For example, MJ and B, if we wanted to extend MJ, which is the first element of L2, by B, then we know right off the bat, we know that this cannot be part of C2, C3, I'm sorry. Why is that? Because M comma B doesn't belong to L2. And by downward closure, we know that if this was large, if MJB was large, then every subset would have to be large. But this is not the case here. So we can disqualify this combination and every other one using the downward closure property. So again, a lot of pruning is going on in these repeat until iterations. So it turns out that now the a priori algorithm terminates with L1 equal this, the frequent one item sets, and L2 is this, the frequent two item sets. And now one can go back and do the phase two, which is quite inexpensive, right? And easier to program, if you like. You just take every large item set, you subtract one element over here, and you count the supports. And if the supports exceed the minimum confidence, which is also part of the input, then you discovered your association rule. Okay, I think this is what I want to mention pretty much today. I know it's late in India, so I appreciate everybody staying up late to listen to me. I hope I gave you a quick overview of data mining. I tried to at least demonstrate in more depth two of the six data mining tasks that I mentioned. The 6 data mining tasks. That list is quite important because it describes the discipline of data mining at a high level. And so I try to focus on two of the 6 and to illustrate them with at least one algorithm and at least one fully worked out example. Maybe I can show one last thing here. There is this book that I particularly like. There are many books, but there is this one that I particularly like. It's called the top 10 algorithms in data mining by Shindong Wu and Vipin Kumar. So what I want to go is here, look at this here. So C45 is ID3. K-means is a well-known clustering algorithm. Support vector machines is another technique. A priori is the one we discussed. EM is expectation minimization. PageRank is a well-known algorithm that is also categorized as a data mining algorithm. PageRank is a famous algorithm, as you know, that resulted in a billion-dollar company. The Google company and the inventors of these algorithms also became billionaires. ADA Boost, KNN, K nearest neighbors, naive Bayes, and CART, classification and regression trees. These are the top 10 data mining algorithms according to this book. It's a very good selection. And at least I was able to present to you 2 of them, so the ID3 and the a priori. So I'm by the way, I'm happy to share all of these materials, including this book and other books on practical data mining. So let me just show one of them and finish. I do want to show you this one here. I'm sorry. Yes, this one. Sorry. This one here, data mining, practical machine learning tools and techniques. This one is particularly useful because it's related to a free data mining software called Weka. Let me see if they have a description of Weka. No, they don't, but anyway, Weka is a university in New Zealand called Waikato Environment for Knowledge Analysis. Weka is a free data mining software that you can download online, and this book here tells you how to use it. you can run all of these algorithms that we talked about and a lot more data mining algorithms for free for medium-sized data sets and make assignments for your students and so on. Okay. So let me just share one more thing. I promise this is the last one. This is WECA, University of Waikato in New Zealand. So it is a machine learning toolkit. It's also a bird in Australia. So it's not accidental that they named their software after this lovely bird over here. So this is the kind of data that you can enter into WECA. So it defines a flat file format called ARF. And this is what it looks like. You describe your attributes, and then you have your data in the usual database format. Okay. And after that, this is the opening screen of WECA. So you can maybe show some. Let me see here. I want to show you a specific example. These are all the parameters that you can set to run a data mining algorithm on your data. For example, here, this is a decision tree. This is the J48 pruned decision tree that you can automatically find from your data. And here it is. So this is produced automatically. The decision tree from your data is produced automatically in this free software, and you can use it to do classification and so on. So thank you very much. I will stop here. I really appreciate your time. And again, I'm very honored that I got invited to this wonderful event. Thank you. If there are any questions, I'm happy to answer.
You can discuss with the professor. Dear participants, you can ask questions. Dear participants, you can post your question in the chat box. Madam, mic unmute பண்ணுங்க. எல்லா மைக்குமே. Participants, you can unmute your mic as well as video and ask questions.
I see somebody is asking to share the book. I'm happy to do that. I can email it to Professor Chinia and go from there.
No questions. Respect professors. Accepting our request to be part of this 6 days Atal FDP program. You have joined with the Indian learners and innovators. More than 500 learners and professors were attending your session for more than 1.5 hours. You have clearly discussed about the concept of data mining and the databases. You have said that what is the difference between data mining and databases. And you have discussed about the application of the probability in data mining and association rule complexities. And you have discussed about the machine learning machine learning concepts introduced available in data mining and the new software tools available for data mining. All these things are very useful for professors, learners, and researchers. Thank you very much for this wonderful contribution from your side, sir. You will have a continued association with you. Whatever the materials you share with us, we will share with the participants. And I request you to share your email ID, sir. Then participants, if they want, they can have any further discussions. Thank you very much, Professor.
You,
Thank
sir.
you very
Thank
much,
you.
audience. Thank you all.
Thank you.
I request all the participants to switch on your camera for the photo session. Dear participants, kindly switch on your camera for the photo session. Thank you, Professor. All the participants, please switch on your cameras for taking photos. I request all the participants to switch on your camera for the photo session. Participants, kindly switch on your camera for the photo session. Hello, camera. Thank you, participants. Thank you. Thank you, Professor. Thank you, Professor, for joining with us. Thank you.
Thank you very much. Thank you.
Dear participants, the feedback link for the session 2 is already posted in the chat box. So all are asked to fill your feedback by using the Atal registered email ID. Thank you. Thank you for your valuable presence. Thank you, one and all presenting over here. Dear participants, kindly fill your session 2 feedback by using your registered Atal email ID by using the SJCA Atal ID. Okay. Once again, I request all the participants to fill your session 2 feedback link. All the participants are asked to fill your feedback link for the session 2 by using your Atal registered email ID. Dear participants, thank you for your valuable presence for the day 1 FDP, and we will meet you by tomorrow shortly at 6 p.m. for the day 2 sessions. Thank you all.